Okay. We begin our lecture 14. Today's topic is about p-value method. So we're still trying to do hypothesis testing, which means you make an hypothesis about the entire population and try to see if that hypothesis is true or not by taking samples and making judgment from them. Okay. Last time I showed you how to figure out the critical value and find the rejection region, and by calculating the z-score or the t-score and seeing if the z-score or the t-score falls into the rejection region or not, we were able to draw statistical inference. Now today it's almost the same, except that we do something called the p-value. Now p-value method kind of fell out of favor recently, so in a lot of places they don't teach this anymore because it was kind of abused. P-value basically says how significant your research is, and yeah, so let me start by explaining what the p-value is, and then I'll continue what I mean by that, right? Okay, so instead of finding the critical value beforehand, one can calculate the p-value of the sample mean. Suppose z-score is calculated by z equals to the sample mean x bar minus mu, which is the population mean, divided by sigma over square root of n. The sigma could be replaced by s sub x if you only have the sample standard deviation. But anyways, if that's so, then depending on whether h1 is two-tail, left tail, or right tail, the p-value is defined as follows. So if you're trying to use the p-value, then the two-tail would be, if your h1 is two-tail, then and if your z-value is positive, then you're trying to see how significant the rejection region, or how do you say it, the outer bounds bounded by your z-score is. Okay, so you're trying to figure out the area of the z-score that you calculated. Okay. So in other words, this is trying to say, what's the probability that you get your test statistic number this high? And because in continuous probability, you cannot talk about probability of one point. You have to say probability of some interval. So you start from that and that number and above. So suppose your z-score is like 3, then you're trying to say, what's the probability that your z-score could be 3 or more, or also -3 or less? If you're doing two-tail test, then you're doing the both. Okay. What's the probability that your z-score could be 3 or more, or -3 or less? Okay, that's how you talk about the p-value. And notice that in the two-tail part, it's doubled, right? Because there are two sides, and these are symmetric. Now, if you're doing left tail, then your p-value is simply this area on the left side. And because the norm CDF function gives you the area left of your z-score, you just have to apply the norm CDF, and that's it. Okay. And if it's a right tail one, then the p-value is 1 minus norm CDFZ, because for something positive here, the norm CDFZ would give you this white area, right? But you really want this orange area, so you have to do 1 minus this white area, which gives you this orange area. And again, this would be like if your z-score is, say, 2.5, then that orange area would be answering what's the probability that your z-score could be 2.5 or more. That's what p-value is saying. Yes?
So that red area, is
Hmm?
that like the rejection area still?
No, the rejection area. So the question was, is this same as the rejection area? Actually, it's not. What really happens is that your alpha value, your significance value, or significance level, gives you the rejection area. And uh, if your z-score is higher than your significance, no, if your p-value is smaller than your significance level, then what happens is that this orange area will be inside the rejection area. So I'm a little afraid to draw anything on here because they kind of crash. But let's just say that this is like the rejection area. If this is a rejection area and your p-value happens to be smaller than the significance level, because rejection area is defined by the significance level, but the p-value is defined by the z-score, your test statistic, okay? And if your p-value is smaller than the significance level, you end up having this orange one inside the red zone, which is the rejection area. Does that make sense? Kind of. All right. Yes.
When you said that p-value gets abused, like what is that? What did you mean?
So yeah, so I was saying p-value gets abused. All right. So so that in biology research, health research, and a lot of the sciences, uh, p-value kind of tells you how significant your research is. So think of it like this. If your p-value is very small, like 0.01%, then something extraordinary has happened, right? Yeah. So it's like this. Under the assumption of the null hypothesis, let's say you calculated your p-value and that became 0.01%. That's extraordinary, which will blow up the conventional wisdom, and that can prove something that people didn't know about, right? So people always get concerned about p-values. If they do an experiment and they get a p-value that's lower than 5%, and suddenly, yes, we got it. We have something to publish. But then if the p-value goes above the 5%, they're like, oh, okay, we didn't make it. So this experiment bombed. The result of that is we have something called drawer effect, which means researchers would do a bunch of experiments towards to their goal of proving certain things. And what happens is that if they do an experiment and the p-value became above the threshold, so it's not that significant, they would just put it in the drawer and then forget about it because nobody can publish. And then people who, for experiments which by chance did reach that threshold, it went below the 5%, then suddenly they're happy because now they can publish it, right? So that's how people began using these p-values to like determine how worthy a paper is. And the downside of that was that if you run experiments over and over again, and let's say your threshold was 5%, that means if you run 20 experiments, you might have one going below 5% just by chance, right? And you might end up with a result which you honestly did all the work and all the results were correctly reported, but it could have been just a statistical fluke. And that still goes into the papers. And that is actually one of the problems in modern science, and especially in places like biology, because in biology you have very complex systems, right? So there are so many other factors you can't control, and you get some result and you might get a result which you didn't expect, right? And Some say that like a third of papers on Nature, which is like the most famous science paper, science journal on for all things science, right? Uh, they say about third of the paper in the Nature is probably not reproducible, meaning that if you took the result and took it to the lab and tried to do it again, you will get a result which doesn't agree with what the paper is claiming. Uh, yeah, so that's the problem. So uh, to to undo this drawer effect, people try to pay less attention to the p-value, but they try to see if they can publish both the ones that reach the threshold and the ones that don't prove anything. They might still be worthy of publishing and stuff like that. Okay. All right. So now, once you get the p-value, what does it mean? I already explained this, but it's good to have it in a slide. So if the p-value is smaller than the significance level, then the test statistic, the z-score, is inside the rejection region. So in such a case, we reject the null hypothesis. And if the p-value is greater than the significance level, then we see that the z-score will be outside the rejection region, and we do not have sufficient evidence to reject the null hypothesis. So in order to see how this is done, let's do an example. And much of the things that we do here will be similar to what we did in the last lecture. The only difference is we just calculate one more thing, which is called p-value. And when you use p-value, there's no need to do inverse norm or inverse t. Oh, by the way, there's one more thing. If you don't know the standard deviation of the population, which is most likely the case, and if your sample size is below 30, then you have to use the t distribution rather than z, and you have to use not the norm CDF, but TCDF here. Okay, so it's the same formula, but all the normal distribution is now replaced by t. So maybe I should note that here as well. Okay, so I want to say, note if population standard deviation is not known and n is greater or equal to 30, no, less than 30, then one has to use t distribution instead, which means instead of norm CDF, we use t CDF in the calculator. Okay, so I think we'll have an example like this, right? Okay. Oh, yeah, actually, this one you have to use t distribution. All right. Example, the nicotine content in cigarettes of a certain brand is normally distributed with mean in milligrams mu and standard deviation 0.1. The brand advertises that the mean nicotine content of their cigarettes is 1.5 milligrams. Now, suppose a reporter wants to test whether the mean nicotine content is actually different than advertised. So he takes measurement from a simple random sample, SRS means simple random sample, of 15 cigarettes of this brand. The sample yields an average of 1.4 milligrams of nicotine. Conduct a test using a significance level of 0.01. So let's see what we can do here. So whether you use the p-value or the method we described in the last time, you have to decide what kind of hypothesis you're trying to test. So the very first step is you have to find out what H0 and H1 is. And to figure out what you want, you should read it and see what you're trying to show. if you read it, you see that the mean nicotine content is actually different than advertised. That's what you want to show, right? Since it says different, is it a two-tail test, one-tail test? Or if it's one tail, is it the left tail or the right tail? What do you think? It should be two-tail, right? It's two-tail because it's different, right? If you want to prove if something is more, or if you want to prove if something's less, then you wouldn't use one-tail test, right? But if it's simply different, you use two-tail. All right. Okay. So we take that as the alternative hypothesis, two-tail test. And the opposite of this would be the H0. So, and as I said, H0, the null hypothesis, is always stated as equal. So you write down mu is equal to 1.5. So that's what the company claims, and you want to disprove that, right? You want to say that no, something's off. He doesn't think that's right, right? In fact, it looks like from this one, it looks like the average is less than 1.5, right? Okay. So since we have two-tailed test and the population deviation of 0.1 is given. Oh, okay. So I thought this was a t-test, but it's not because the population standard deviation is given, right? The sigma is given. So we use the normal distribution. So let's continue on. Since it's normal distribution, we call it a z-score. If it's a t-distribution, we call this the t-score. The z-score is the information that we use from the sample to make judgments. So that value in this context is called the sample statistic. And the sample statistic came out to be negative 3.873. Now, let's see what that means. Well, if you take the norm CDF of negative 3.873 and multiply by 2, and as you can see, all I'm doing is I'm applying this case, right? If z is less than 0, the p-value should be twice the norm CDF of z, because you get this orange one if you just do the norm CDF z, but then you have to double it. So that's the formula that we're using. And the value came out to be very small, 0.0001. So can we believe the company's claim that the mean is 1.5 milligrams? Yes? What do you think? If we accept that the company's claim 1.5 milligrams of nicotine per cigarette is true, if we say that that's true, then the chance of this happening is only 0.0001. So 0.01%, right? So do we accept the company's claim? No, because an unlikely thing has happened, right? Yeah, it's very unlikely that if the company's claim is true, then we would get this value. So therefore, since p-value is smaller than the significance level of 0.02, we reject the null hypothesis and conclude that indeed the nicotine content is different from what is claimed. So that's how you do it, and it's basically the same idea, except instead of making judgments by calculating the inverse norm or inverse t of the significance value, you just calculate the probability of the z-score. That's the only difference. All right, so let's do a few more questions. A nutrition expert claims that the average American is overweight. To test his claim, a random sample of 25 Americans was selected, and the difference between each person's actual weight and ideal weight was calculated. For this data, we have x bar equals to 15.2. Sorry. Okay, x bar equals to 15.2, and the sample standard deviation is 28.8. And the question is there sufficient evidence to conclude that the expert's claim is true? Carry out a hypothesis test at a 2% significance level. All right. So let's see. Now, before we do anything, we should start out by figuring out what H0 and H1 is, right? Okay, so what do we want to prove? H1, that mu is, what do we want to prove? Uh, so because you want to prove that that this is true, you want to prove that average American is overweight. That's what you want to prove, right? So what should be the null hypothesis? What's the opposite of that? Opposite will be not overweight, right? If you want to prove that something's overweight, the opposite will be not overweight. But then remember that the null hypothesis is always equal. So what's the statement that you should put for H0? Which American is, rather than saying underweight, no, just has okay weight. I don't know what to say, right? So correct weight. Okay, okay weight. All right, and then that's like saying mu is equal to 0, because see, um, the data collected is the difference between the actual weight and the ideal weight, right? So because you subtracted the two, if it's 0, that means it is ideal weight, right? Okay, so yeah, I guess the better way is to say ideal weight, right? Okay, and then the one that you want to prove is overweight. Okay, how do you say that in terms of the mu? Greater than 0, right? Yeah. Okay, so that's what kind of test? No, is it two-tail test, right tail test, left tail test? Right tail test. Okay, is that good? So you're doing right tail test. Right. Okay, now let's calculate these things. So first, the value of the standardized test statistic. So what do? That's the z-score, right? So z-score is the difference between x bar and the mu divided by sigma divided by square root of n. And in our case, x bar is 15.2. And then what's the mu here? What's the mu here? 0. Because that's what the mu value in the null hypothesis is, right? So this mu value that you use for the test statistic should always be this value that you get from the H0, okay? And then sigma is, well, we don't have the sigma, so you need 28.8, right? Oh, by the way, so that means we actually have to find the t distribution, right? Because we don't know the population standard deviation. We're just using s in place of it, right? S sub x. Here it's just given as s, but it's yeah. All right. So you really need to, you're using s in place of the sigma, so that means we need to use the t distribution, and then we need the square root of 25. Yes, you have a question? Yeah, the question is it right tail because it's overweight? And that is correct. Yeah, because you're trying to prove that mu is bigger. If the statement says mu is less, then it'll be left tail, right? If the statement says, so if your H1 says mu is not equal, then you use two-tailed. Right? All right, so let's use this, 15.2. And when you do this, please use parentheses. I think the number one mistake people make when doing this calculation is that they forget to use the parentheses properly. And even if they have all the work done correctly, they end up doing it wrong. Okay, so put another parenthesis here because this is the top and the other one was the bottom. For each, the numerator and the denominator, please put parentheses around it. Missing that one would cost you. All right, and then divide it by square root of 25. But I could put that in, but I know square root of 25 is 5, so I'm just going to do this, right? So I'm going to put enter, and you get 2.639. 2.639. Okay. 2.639. Okay, now rejection region for the standardized test statistic. Okay, so this part B is what we did last time. How do you get the rejection region? Well, you have to know the boundary. Okay, so the boundary of the rejection region is determined by what? It's determined by the significance level. So you have to apply the inverse t or inverse norm to the significance level to get it. And because this is a right tail test, you should be doing, well, let's try to draw a picture. So it's like you have this t distribution, and we have a right tail test. So the right tail, so the rejection region is only on the right side. But then your significance level is 0.02. We have the significance level as 2%, right? So that's what we want. That means on the left side of this boundary that we want, so we really want to know this spot right here, right? So the left side of that boundary, this question mark will be the boundary for the 98th percentile. Does that make sense? Because this much is 2%, this much should be 98, right? So you're looking for the 98th percentile. And remember, this is a t distribution. So how do you do it? So let me first copy this and paste it on the slides. Okay, copy. All right. Okay. So that's what we're trying to do. All right. So let's try to do inverse t. Because that's a t distribution, we have to do inverse t. Inverse t. Oh, but wait. For the, okay, so first area is 98 percentile. Okay, so we put 98 there. But wait, what's our degrees of freedom? 24. Why? 25 minus 1. Since the sample size is 25, we put degrees of freedom as 24. Then we are going to paste it. And that gives us 2.1715. 2.171. Okay. So 2.171 and after. That's our rejection region. Okay. So in other words, in terms of a how do you say it? An interval. It's like this. As an interval, it's starting from 2.171 until infinity. You know how to write interval notation, right? So this is the interval. That's the rejection region. Okay. All right. So already you kind of know which one wins. So your t distribution, the test statistic t-score came up as 2.639, and your rejection region is 2.171 until infinity. Okay, question. Is 2.639 inside the rejection region or not? Yes. 2.6 is above 2.171, so it does belong to this interval, doesn't it? Right. So if it's inside the rejection region, what's our conclusion? What's our conclusion? If it's in the rejection region, what do? We reject the null hypothesis and we adopt H1. So there is sufficient evidence to prove that average American is overweight, yeah, including myself. Yeah, I'm trying though. All right. Okay. Huh? No, no, just by eating less. All right. Okay. But let me before we actually so we actually know the answer for D, but I'm going to continue on and find the p-value instead. Okay. So what would happen if we instead adopted the p-value approach? Well, for the p-value approach, you need to know what is the area from 2.639 and afterwards, right? So what you do is here you use TCDF, but know that TCDF of 2.639 would give you the area before 2.639. You want the one that's after. So what should we do after doing TCDF? You subtract from 1, right? So you have to 1 minus TCDF of 2.639. And of course, you have to provide the degrees of freedom. Okay. So let's see what that gives us. Second vars, TCDF, there it is. And don't touch the lower. You're just going to put the upper there, and that's 2.639. Degrees of freedom is 24. Enter, and you get 0.9928, right? So you do 1 minus 0.9928, and oops, what did I do? Oh, sorry. 1 minus 0.9928, and that gives you 0.0072. Okay, so that's your p-value. Now, question, is this less than the significance level? Yes, right? P-value is less than the significance level. Significance level is 0.02. So what? I use this calculator right here. I did 1 minus TCF. I just plugged this into the calculator to get this value, right? And the significance level is 2%, so it's 0.02. Yeah, you have a question? Hmm? Question was, we didn't do the CDF last time. You're correct. We did not do CDF last time. You only do CDF when you're trying to get the p-value, right? When you're trying to find the critical value, use the inverse. Okay, so let's inverse norm or inverse t depending on which distribution you're using. Okay, so let me say this again. This is really important because you're going to be confused. All right, when do you use the inverse? When you want the critical value, the z alpha over 2, right? Or t alpha over 2, that's when you use the inverse. When do you use the CDF? When you're trying to find the p-value, all right? So let's make sure that you understand that. Okay, so we're using the p-value here. And then finally, our decision for the hypothesis test is that we have sufficient evidence to prove that average American is overweight. So that's the answer for this. Okay. Any other questions? All right. Let's do the next question. A pharmaceutical manufacturer is concerned about the impurity concentration in pills, and it's anxious that this concentration not exceed 3%. So if they sell something and their impurity becomes more than 3%, then the customers, they don't like it, and your sales will go down. It will plummet. Yeah. Now, it is known that in any production run, the impurity concentrations follow a normal distribution. Okay, that's good to know, because now we can use statistical testing. A random sample of 25 pills from a production run was checked, and the sample mean impurity concentration was found to be 3.07%, and the sample standard deviation was 0.4%. Test the null hypothesis that the population mean impurity concentration is 3% against the alternative that is more than 3%. Use a 5% significance level. Answer the following and round off your answer to 3 decimal places. All right, so it's a lot that's written here, but let's try to simplify things. So it's really saying the following. N is 25. You see that, right? N is 25. And what is the sample mean? What's our sample mean? 3.07, right? And what's our standard deviation of the sample? 0.4. Okay. And what's the null hypothesis? What's the null hypothesis? Is equal to 3%, right? What's the alternative hypothesis? Yeah, so you're worried that it's more, right? So you want to show if it's more or not, okay? So you want to see that mu is greater than 3, which means this is, again, a right tail. All right. Okay. And what's our significance level? I deleted it, was 5%, right? So you say what? Your alpha, which is the symbol for the significance level, this is 0.05. Okay. All right, so let's use this to find all this. Again, the sample size is 25. I should have made this higher, but again, we're stuck with the t distribution, right? Because we only have the test, we only have the sample standard deviation. So t would be 3.07 minus the h0's assumed mu, which is 3, and you divide that by 0.4 divided by the square root of, let me see, of 25. Okay, and let's use the calculator to see what that is. All right, so we have parenthesis 3.07 minus 3 divided by open parenthesis and 0.4 divided by square root of 25 is 5, so I'm just going to use that. And that gives you 0.875. Okay. Now, what is the critical value? That's just asking for the boundary of the rejection region, right? So you have to do inverse norm, okay? No, you have to do inverse t, right? And because it's the right-tailed one, you have to use 1 minus inverse t of, yes? We'll begin soon, okay? All right, and then we have degrees of freedom 24, so let's put that in. 1 minus, and then inverse t, 0.875. df is 24. And we're going to put that in there, which gives you, oh no, just a minute. That's not how you do it. Sorry, I got it backwards. This shouldn't be that. is simply this, right? Sorry about that. So second vars inverse t. So we know that, no, I'm using, sorry, I messed up because I'm using the test statistic, right? Use a test statistic to get the p-value, and to get the critical value, you need the significance level. So our significance is 0.05, and if you have 0.05 from the right side, then the left side will be 95%. So that should be the one that I use. I'm sorry, I was a little bit in a hurry. So you have a question? You would divide that by 2 if you're doing two-tail test, but here we are using right tail, so there's no need to do that, okay? So you have 1.71. Okay, so question. That's the last question. Please let's finish, okay? Uh, can the null hypothesis be rejected at 5% significance level? Why not? Our test statistic, is this in the zone? No, because this and above, it's the right tail. So this number and above is the rejection region, and this is below that, okay? So the answer is no. So the answer is no. There is insufficient evidence to reject the null hypothesis. And that's it.